Okay, today we're going to talk about vectors. So in order to talk about vectors, we first have to remind ourselves about arrays, because vectors are basically very similar to arrays. An array holds a collection of items that are all of the exact same type. And the benefit of this is that the whole collection of data has a single name. Right? And we've seen these already. If I wanted, for example, 10 floats, I would do this kind of declaration here. This says, when the flow control gets here, go carve out room for 10 floats and give the entire group of variables a single name, ARR, for array. Okay, to access data in the array, use the name of the array and an offset from the beginning. Right, so if I said ARR at position 2 is equal to 10, what we know is when the flow control gets here, we're saying go find a thing called ARR and go to position 2, which is actually the third item in the array here, and store a value. In this case, we want to store the value 10. Okay, and of course, this will change just a single float. The square brackets notation gives you access to just a single element in the collection. So the real power of arrays is that you can process all of the elements in a loop. And the same loop code can be used to process 10 elements or 100 elements or 100 million elements. Right, so again, this is a little loop here that's going to zero out all the values inside the array. But if there were 10 or 100 or, like I said, 100 million, the loop code would not look that different. Okay, and that's a really powerful thing about arrays. However, there are some problems with arrays. Let's talk about the problems. First of all, arrays always have a fixed size. The size of the array is determined at compile time. So the size of an array can't be changed while the program is running. If you fill up an array and decide you need more room, at least from what we know about right now about C++, we're kind of stuck. Okay, we can't make the array any bigger. So it might be nice if we could do something like this, where if we fill up the array, for example, we might want to prompt for a new size, and then say, well, go create an array that's exactly that size. Okay, this is a problem, okay, and this will not compile, because the size of the array in the declaration must be known at compile time, not run time. So compile time is the time when you hit the magic compile button, and runtime is when the program's actually running. So the compiler has no idea what value the user is going to enter in, so this is going to generate a syntax error. Okay, now there is a way around this. The solution is to use something called dynamic memory, but we're not going to be talking about that in this class. Dynamic memory, however, will be front and center in another class called data structures, which is logically the next class that you would take. But for right now, we're kind of stuck. So if you do use arrays, you usually set aside enough room in memory for your worst case scenario. So for example, I've never taught a class with more than 40 students in it. So if I was writing a program to store student information, I might choose to do something like this. Okay, so here I have my student data type. This is, again, just maybe a struct or a class that I built that holds information about students. And this says I want to go carve out room for 40 student objects somewhere in memory. And I'm choosing 40 pretty much certain that I'm not going to use all 40 of them. So it's pretty common for me to have a class with maybe 8 students in it. Okay, but I'd still have to kind of program for my worst case scenario. And in this scenario, I'm only really using maybe 20% of the elements in the array. And I'm wasting 80% of the memory set aside for that array if I have a class with 8 students in it. So this is not a good use of precious memory. Now, memory has always been and probably always be a precious resource. As soon as manufacturers create larger and larger memories, we programmers have a tendency to gobble it up and use it. Okay, so memory kind of is always this precious resource. resource. It's definitely finite, but we programmers tend to find all kinds of ways to use it as soon as we get more. Okay, so that's the first big problem, is that the size of the array is fixed. Okay, we also have these bounds problems that you can very easily go outside the bounds of an array. Right, so if we go back to this example where we have an array of 10 floats, we know the index values are from 0 to 9. But if I do something like this, say ARR at position 10, okay, I'm going to be outside the bounds of my array. So the index values here are from 0 to 9. And now if I say, go to the array at position 10, right, and store the value 100 there, the program will dutifully go find array, move over the size of exactly 10 floats, and then put the value 100.0 right there. Okay. In C and C++, you may not get any indication that something bad happened here. Okay, the program will just happily go 10 elements away from the beginning of the array and store the value there. So we know from previous examples when we talked about arrays that we could be stepping on some other piece of data when we go outside the bounds of the array. So maybe there happened to be a variable that happened to land right here. Maybe it was called age. And maybe before it had the value of 40, but now we just stepped over that value and put in 100. Okay, this is very dangerous. This is a very hard bug to find. Okay, and our last big problem with arrays is arrays don't know their own size. So look at this code here. We declare an array of 10 items, and then we have 2 loops to process the array. So first we zero out all the values, and then we go and print out all the values in the array. Notice the hard-coded use of 10 here. There's a 10 here, a 10 here, and a 10 here. All of the hard-coded 10s in the loops always have to match the 10 in the declaration of the array. If I change the size of the array, okay, so let's say, I've changed my mind. Now I want this to be, 20 elements. Well, now I have to remember to change that condition in all the loop tests that iterate over the elements. So I'd have to remember to go to this one, and, it's pretty likely that you're going to miss one. Okay. So you might think, well, why don't we, instead of using the hard-coded number, why don't we just create a variable that we used in both the declaration and the loop tests? Okay. So that'd be smart. That's a good idea. Unfortunately, this will not work. And this has to do with the first problem we talked about. The size of the array has to be known at compile time, not runtime. So this is a variable. In theory, this variable could change from the point of its declaration to the point of its use here. So we can't do this. Now luckily there's kind of a fix. We can use this type of variable called a const, or a constant. Okay, and a constant variable is one where you get one and only one chance to assign a value to the variable. So this says const int size of array is equal to 10. If I tried to change the size of array anywhere else in this program, I'd get a syntax error, because the arrays, or because the int is declared constant, it can only be set once here. Okay, this is okay because now the compiler does know the exact size of the array at compile time, and this code would compile and run. So notice now we're not using a hard-coded number anymore, we're using size of array. And if I wanted to change something, I would just go here, change it, and recompile the program, and now all of a sudden all my loops would magically be updated. Okay, although this is a good solution, it's not a great one. So for example, now if we want to pass the array to a function, we're also going to have to pass around this constant variable that goes along with it. This is not a huge deal, but it seems like if arrays were just a little bit smarter, we wouldn't have to bend over backwards to use them correctly. Okay, and that's where the vector comes in. A vector is an intelligent array. Vectors solve all the problems we just talked about. To use a vector, you must !include vector at the top of your program. This imports the code from the vector library. Also make sure you have the using namespace std at the top of the file. Now vectors use a syntax feature called templates, and we're also going to be discussing templates a great deal in that next course I mentioned called data structures. But for now we won't worry too much about them. When we declare vectors, though, they are going to look a little bit different from other data declarations. So let me show you the declaration of a couple of vectors. Okay, so there is a type called vector, and what we're doing here is we're creating a vector of integers called intvec. And here we're creating a vector of strings called names. So whenever you create a vector, you're creating a collection of things. Just like an array is a collection of things. We're going to store things inside the vectors, okay, just like we store things inside the array. Now you can have a vector of any valid type. So if you can create one item, always know that you can create a vector to hold many of them. And really there are two ways to create a vector. We can create an empty vector, or we can create a vector with some initial size. We'll start with the empty vector. If a vector can be totally empty, there must be a way for us to add an item to it as the program is running. Okay, so we're going to be talking about how to add to a vector. The way we do this is with the pushback method that belongs to the vector data type. So a vector is an example of a user-defined data type. It includes data and methods that work on that data. Now we're going to be discussing creating our own user-defined data types in this class very soon. And a vector is just an example of one. Okay, so let's look at a picture here. So we've started by declaring this vector called vec1. Right? And right now it's totally empty. Now the way we add to the vector is, like I said, we're going to call this method called pushback. And then we're going to pass in a piece of data to this method. This is what we're going to add to the back of the vector. Okay. So vec1 started out as empty. Then we called vec1.pushback with the value of 10. And that means that the value 10 now is at position 0, very much like an array. All these elements have an index number. And then when I call vec1.pushback with 20, the value 20 gets pushed to the back, and now we have two elements with index value 0 and 1. Okay, pushback always adds to the back of the vector, because if it were to add to the beginning, then all the elements would have to be shifted over. So let's imagine what would happen if we were able to push to the front of a vector. Okay. So here, let's say we were going to do something like pushback 30 to the front. Right? So what would we have to do if we were going to add this value 30 to the front? Well, the first thing we'd have to do is create some room for a new item, and then we'd have to start shifting all the values over, because we don't want to lose the 10 and 20 that are already in there. So we would shift the 20 over, we would shift the 10 over, just to make room so that we could store the 30 there. Okay, all of that shifting is just more work for the processor to do. If we can avoid it, we definitely should. It's much more efficient to just add to the back of the vector. rather than the front. So again, if we were going to push something to the back of the vector, we still have to make room for that additional item. But then we can just store the value 30 there. We don't have to shift anything over. We just extend this a little bit and add the new value there. Now, if you absolutely must insert in the middle, there is a method to do that. It's called insert. However, keep in mind that all the elements after the item you're inserting will need to be shifted over to make room for that new element. If you have a large vector, this can be a pretty expensive operation. So generally, you want to try to avoid using insert and try and use pushback as much as you can. However, there are times when it will make sense to use insert. Okay, when you push something to the back of the vector, that always makes a copy of the data being pushed. So let me show you what I mean here. So here we have this integer called x. We store the value 10 in it. We say vec1.pushback x. This will make a copy of x. This will take the value 10 and put it on the back of the vector. If in the very next statement I were to change the value of x to 20, that is going to have absolutely no effect on the copy that got pushed back to the vector. Okay. So keep in mind, pushback is really copying a value to the vector. And if you change a variable, in this case x, it is going to have no effect on the copy. Now, how do we access elements? Well, to access the elements of the vector, you can use either the at method or the square brackets notation. And we'll see the square brackets notation is very, very similar to array notation. Okay, so these two things are equivalent. So this says vec1.at 0 means go to position 0. We know there's a 10 there. But this also works just fine. We say vec1 in square brackets, we put the number 1. That says go find the thing called vec and go to the position 1, which is actually the second element. And we have access to that value, which we're going to print out. So we know that that value is 20. Okay, so vectors feel very much like plain old arrays. But from now on, you should always be using vectors, because vectors are smarter than arrays. Okay, so there is an index from the beginning, and you can use the square bracket notation to access the elements. Now, the program will crash if you go outside the bounds of the vector. And believe it or not, this is actually a good thing. At least if the program crashes because you you went outside the bounds of the vector, you will know where to look for the problem. The problem with the silent failure mentioned before is that someone else might think that there's a problem with their code, when the problem is really with your code. The program crashing and burning means that at least you'll know there is a problem with your code that needs to be fixed. Okay, now that second vector, vec2, already has room allocated for 10 elements. Okay, so let's go back here and remember this declaration. This also says create a vector of integers, so call this one vec2, but make sure this one has 10 spots in it to hold data. Now it turns out all 10 spots have an undefined piece of data in them. So you definitely don't want to use these until you set a good value. So if we were to kind of picture this, this is what vec2 looks like. There definitely is something in memory called vec2. It definitely has 10 elements, in this case 10 integers. But the values inside those integers are undefined. What that means is they're garbage values. They definitely are integer values, but we have no idea what they are. They might be 0, they might be 100, they might be 100 million. Okay. Until we set a value for them, they're essentially garbage. Okay, so let's put some good values in the vector. Okay, so this is how we would do that. So we have a for loop here, And we're going to say I is going to start at 0, and we're going to say while I is less than vec2.size. So notice the vector knows exactly how many elements are in it. Okay, we no longer have to store the size in a constant variable and pass it around with the vector. The vector is now smart enough to know, in this case, there are exactly 10 elements set aside for this vector. Okay, what this means is we can pass a vector to a function, and it will know how many elements to print. So here's a print int vector that takes a vector of ints by reference called vec. And now whether we pass in a 10 element integer vector or a 10 million element int vector, this function will work for both of those pieces of data. Okay. You'll almost always want to pass your vectors by reference, because they can become quite large, and passing by reference is much more efficient than creating a copy of the vector. Now in addition, vec2 can grow while the program is running. So remember, vec2 started with those 10 elements. We just basically zeroed them out here. So the first 10 elements have 0 in them. But we can also push back 1, 2, and 3. And now our vector would look something like this. If we were to call our print vector function and pass in vec2, this is what we would see. The first 10 would be zeros, and then we'd have 1, 2, and 3. Okay, so based on the examples, it should be clear that vectors solve all three problems. The fixed size problem. The vector can grow as the program is running. It can also shrink. There's a pop back method that removes the last item from the vector. Occasionally that'll come in handy. The bounds problem. The program crashes if you go outside the bounds of the vector. And believe it or not, that's better than nothing happening or having this kind of silent failure. And lastly, the size issue. The vector knows exactly how many elements are in it. You just ask the vector its size, and it will tell you how many elements are currently being stored. Okay, so that's the C++ vector. And like I said, from here on out, you're not going to want to use plain old arrays anymore. Vectors are better. They're like arrays. You get all the benefits of arrays, but they're smarter. You get some additional functionality. So you should always be using vectors from here on out.